Welcome to this DVCon 2023 presentation on Demystifying Formal Test Benches, Tips, Tricks, and Recommendations. In this presentation, we'll cover formal test plans. We'll take a look at what the similarities and differences are between a simulation test bench and a formal test bench. Then we'll dive into what the components of a formal test bench are. We'll cover some advanced topics, some considerations when architecting your formal test bench, and then how to know when you're complete. And then we'll wrap up with a summary. Let's take a quick look at formal test planning. Test planning is an integral part of your property checking planning. There's a 7-step flow you can follow. You want to identify the blocks that you're going to verify with formal. Then you're going to describe the spec. You're going to develop the requirements from that spec. And only then do you write your properties. Once you have your properties in place, then you're going to strategize what type of formal test bench you're going to use and the coverage metrics you're going to collect. Test planning is done when you're doing formal test planning, simulation test planning, emulation at the beginning of the project. And you're picking which parts of the design you're going to verify with formal. You're going to write the test plan, and typically that's put in some kind of spreadsheet. You're going to give names, what types of components, what your expected results are, what types of things you're checking. And then, of course, your properties are going to come out of this and then be back annotated into the test plan when you run property checking. Most design and verification engineers are familiar with simulation test benches. So let's take a quick look at some of the commonalities and differences between a formal test bench and a simulation test bench. From a conceptual perspective, simulation test benches and formal test benches are very similar. With any verification, you require two models. You're comparing two models to see if they're equivalent. And if you look at a simulation setup, there's going to be some kind of sequencer which goes through a driver, which is applying vectors or stimulus to the design under test, and then the outputs are being monitored. Those same inputs are being driven into a second model, and then really what you're doing is comparing the outputs of the two models to see if they're the same. If they're the same, then you get a passing test bench. If not, you get some kind of failure. So of course, in simulation, everything's vector driven. From a formal perspective, conceptually, it's the same thing, although the way formal analyzes things is it's analyzing all possible inputs. So the full input state space is being analyzed, and then that's being refined with some assumptions and constraints. So all possibilities are being applied to the DUT, as well as the modeling code and properties. So the second model in formal really is the modeling code and the assertions that are being checked. And of course, given some input stimulus, you're getting a proof or a counterexample is the result that you're getting out of the formal run itself. So the results are coming out of the properties, the assertions themselves. So conceptually, things are very similar between the two test benches. How they are implemented could be quite different, of course. If you compare formal and simulation test benches, formal will synthesize your design, so you need synthesizable RTL. Simulation, of course, can have behavioral models. Property checking needs properties, so that's required and highly recommended in simulation as well. Formal explores the full input state space, whereas simulation is going to drive specific vectors. Formal can make use of assumptions to limit the state space that's being analyzed, so get rid of the illegal state space. And simulation, it's very specific with the transactors. The second model in formal, of course, is the properties, the assertions, and the modeling code. And then you have some kind of second model in the test bench, so C model, UVM, etc. With formal, your property or assertion is proven or has a counterexample. With simulation, the test bench is a pass or fail type of mechanism, and properties are also pass and fail. There's different implementations you can do with the formal test bench. Typically in simulation, the DUT is instantiated in the test bench. From a ports perspective, the formal test bench just monitors all signals, inputs, outputs, internals. The test bench drives inputs and monitors the outputs. We'll take a look at the two primary ways a formal test bench is implemented. The first one is very similar to how a simulation test bench is implemented, in that the formal test bench is there and the DUT is instantiated within the formal test bench. And of course, as part of the formal test bench, you're going to have your properties, so your assertions, assumptions, and cover statements, modeling code, abstractions. So all of these components are part of the formal test bench. Now, one of the things with formal is undriven inputs, formal can drive directly. And again, it's exploring the full state space, the input state space, cycle by cycle. Now, one of the things you can do is you can pull like your clocks and resets out, or maybe there's some control signals where it makes it easier to verify different modes of operation or that type of thing. So this is kind of dependent on the design that you're testing and how you want to approach it. You can, of course, bring everything out if you want, but typically, only primary types of control signals, for setting up different configurations are going to be pulled up to the top level. Everything else, formal can just drive directly. And of course, you're potentially applying assumptions, on all these inputs as well. The second method, which is probably the more common way of doing it, is you're using bind statements. So you have your design, and then your formal test bench is bound into the design. And this effectively is instantiating the formal test bench in the design, although physically that's not happening, of course. The formal test bench has all inputs, so internal signals within the design itself. The formal test bench is monitoring inputs, outputs, internal signals. All of this comes into the test bench. And then, of course, you have the same components within the test bench, your properties, assertions, assumptions, covers, modeling code, and abstractions. Now that we've seen how a formal test bench can be implemented, let's dig a little bit deeper on what each of the components are that you would put in that formal test bench. Let's take a look at the components of a formal test bench. The first two items here are something that's extremely important for your formal setup, and in most cases will be defined as part of the setup of your property checking tool. The first one is clocks. Formal is a cycle-based technology, so there's no concept of nanosecond or picosecond. If you have a single clock design, there's not really anything you need to do. Formal will analyze the design based on every active edge of the clock, so every rising edge, for example. If you have a multi-clock design, typically you'll want to define what the frequencies are of the clocks, and then based on the active edges of those clocks, formal will do its analysis. So defining the clocks can be extremely important in your formal setup. The other thing that's extremely important is your initialization sequence. So we synthesize the design, and then you need to apply an initialization sequence to put the design into a known good state, and then the formal analysis proceeds from there. Typically, this is just your reset state. So applying your reset, and that initializes the design. Now, some designs, of course, some of the registers won't be initialized. There could be very specific things that you're wanting to do with formal. Maybe there's some bug hunting technique you're doing, so you're going to go into some deeper initial state. But your results are very dependent on the initial state. So if you have some random internal state that you've started from, if you get a proof in that state, for example, it's only as good as its starting state. It may not apply from some other starting state. So in most applications, typically you're starting from the reset state. So all results can come from that. And if you get a proof, for example, from an initial reset state, then it's going to be a good proof under all scenarios that can come from that initial state. If you're looking at counterexamples or bug hunting, then of course the starting state isn't as important, but the bug that you're seeing or the counterexample you're seeing, is coming from that initial state. Of course, you need properties, assertions, assumptions, covers, cover bins. All of these will be used as part of the formal test bench. Modeling code is Verilog code that will help in writing the properties. And then, of course, there's abstractions. If you do have inconclusive properties, then you're going to start to turn to abstractions to reduce state space and hopefully get to a conclusive result. So these are the major components of a formal test bench. Let's look at a few more details. An assertion is a property that checks your design's behavior. So this is what formal is going to analyze against the design itself to see if the behavior is consistent between the assertion and the design. There is complexity to the assertion, so you want to keep them as simple as possible. So for example, here, if you're writing a complex property, it's better to decompose it into simpler properties, which check the same thing. You want to keep the properties as sequentially short as possible. The most optimal is single cycle. Of course, you can't always check everything with that. Also, make use of $rose or $fell. So if a signal is active for some period of time, in some cases you don't want to check starting with each cycle that it's active, but you want to check when that signal started. In simulation, there's the concept of threads. and you launch an extra thread each time the property antecedent starts to evaluate. And so with the rows and fell, you can limit that. Also give them meaningful names. Oftentimes you're going to group properties together, and so if you have names that have meaning, it's easier to group the names with wildcards and that type of thing. So how you name the properties is very important. Also, checking your properties in simulation or emulation can help make sure that the property you're describing is correct. And of course, you're going to back annotate these into the test plan. Assumptions are properties that are used to restrict the input state space that Formal is analyzing. Ideally, you want to keep these as simple as possible. And a lot of times you'll get a counterexample where the waveform you're looking at doesn't have correct input stimulus. So in that case, you would probably want to add assumptions. Most assumptions are going to be global in nature. Now, if there's a signal that you add to it where it's only active for certain periods of time, the term for that is oracle. That's possible as well. So that's a little bit more complicated or advanced. In most cases, when you're just adding an assumption, it's always going to be enabled. But you can gate them, if you will, using oracle signals. Ideally, you want to start with no assumptions, so totally unconstrained design, and then start adding them in as needed. Now, if you have a bus interface, then obviously you may want to put in some verification IP to properly constrain that interface. But minimally, you want as few assumptions as possible. That helps prevent over-constraining, which could hide bugs potentially. Running your assumptions in simulation or emulation is a good idea. Ideally, you will formally verify that the assumptions are correct. If you can't do that because the state space is too big, then running them in simulation and emulation is good. Any assumption that's incorrect, if you get a proof that uses that assumption, then the proof is no good. So you definitely want to make sure your assumptions are correct. And of course, those are going to be annotated in the test plan as well. You're also going to want to write cover statements to check various behaviors of your design. Did the FIFO go empty or full? Did your FSM cover all the different states or transactions? Did your counter overflow? Was there some kind of transaction that happened? So functionality of your design, you want to make sure that you're covering all possible functions using cover statements. This is also critical if you're over-constraining with assumptions. Cover statements can catch those types of conditions. You want to keep things as simple as possible. You just want to use a statement or a sequence. Don't use implication if you can. This will simplify things, or it makes it easier to describe the types of things that you're covering. You also want to keep it simple. So you want a cover statement for each type of condition, not grouping them all together, because then you don't know which one is covering it. You want to make sure that both conditions are there, or whatever conditions are can happen, you want to check them. Again, naming convention is important, and tying it to the test plan is also extremely important. Modeling code is typically Verilog code that simplifies signals that you're going to use in your properties, making them easier to read, and just simplifies the properties themselves. Let's look at an example. So let's say you have a requirement that you can never have more than 5 outstanding writes without having a read, and that you cannot have a read before a write. If you're just going to write this with SVA, it's going to be extremely complex. You're going to use more complex areas of the language. It's easier to just write a counter. So you initialize the counter to 0. If you have a write and not a read, you're going to increment. If you don't have a write and a read, you're going to decrement. Otherwise, you just keep the same value. And so then it's very simple. The property just says my counter should always be less than or equal to 5. If it ever goes to 6, that means you have 6 outstanding writes without a read. You violated the requirement, and you get a counterexample showing that scenario. Or you can say, if my counter is 0, I should never have a read, so this condition should never happen. These two properties actually show 2 important points. When you write a property, you can describe correct behavior, or you can describe incorrect behavior, or behavior that you're not expecting. So using this not here, you're saying this condition should never happen. So both types of ways are extremely useful when writing properties. So you can see here, simple modeling code makes the writing of the property very simple. If at the end of your formal run, you still have inconclusive properties, you may have a state space issue. Formal is exponential in nature, so reducing the state space can get you to a conclusive result, whether a proof or a counterexample. If your design's parameterized, you can reduce the parameters. Classical example is reducing the depth of a FIFO. You can apply constants on the inputs of your design. You can black box irrelevant parts of the design. You can add cut points to cut out complex logic. You can change your initial value. There's certain tool settings where you can maybe abstract counters, memories, or arithmetic constructs. So all of these can be applied, and depending on what the situation is, you would pick one or more of these to abstract parts of the design and or test bench away to reduce the complexity of the problem, and then hopefully get you to a conclusive result. Most of what we've covered so far is fairly straightforward. However, with formal, there's certain things that you can do that you're not going to be able to do in simulation, and it can help greatly in both your formal test bench development as well as what you're going to check. So let's take a look at some of these tricks of the trade. Non-determinism is a mathematical term, and when it applies to formal, what it does is allow formal to control when events happen. So both temporally, so what cycle it's going to happen, and then spatially, what values can be assigned. So very powerful technique that can be used in many ways, which we'll show in subsequent slides. Data independence is another technique. If the data path that you're verifying is independent of the control logic, then you can reduce the complexity down to 1 bit. So maybe 128 bits now become 1 bit, reducing state space. If you have control signals that are constant during a process that's happening in the design, then symbolic variables are a great way to verify all possibilities for those control signals within a single formal run. And then there's a technique here, phantom wires. You can use the antecedent of a property to constrain what's going to happen where formal's controlling wires that are in the design. So we'll show some examples of all of these. Here's an example of a bug hunt to find a bug where a precharge was happening to the same address as a write within 11 cycles, so violating that requirement. I'm using modeling code and non-determinism. So with the modeling code, I can define a vector that is all the DDR signals. I can define some parameters. Then ultimately, I'm defining a couple signals which I will use in my property for when a precharge is happening or a write is happening. I have some modeling code here where I initialize a my write to 0. And there's any number of transactions that can happen, reads, writes, activates, those types of things. But at some point, formal says, this is the write that is going to cause the problem. So it sets this ND bit, and I capture this, set this to 1, and then I capture the bank address. And then in my property, I can say my same pre-signal here is a precharge to the same address that I was using with the write. Now my property is very simple. It says when my write happens, I should not have a precharge to the same address within 11 cycles. And so formal is picking the time, the temporal time, to when to inject this write that would cause the bug to happen. So the internal counters are in some condition that would cause a bug to happen. So this is, the power of modeling code and ND. Data integrity is a classical application of non-determinism and data independence. So you can use just 1 bit to check your data, and what you're going to do is use some modeling code to describe an FSM where ultimately what you're going to do on the inputs is drive 2 1s back to back. Otherwise you're driving 0s. And there's an assumption here on my output of my FSM. I'm just saying the output is driving my data. And the non-deterministic input is start. So formal will pick when these 2 1s are driven back to back such that it will find different bugs in the design. So at some point formal says start, and you're just sitting here outputting 0s, and then you're going to output 2 1s back to back. Then of course there's another monitor FSM where you're checking the output to see that you're getting these 2 1s back to back. So the input to this monitor is my same bit on the output, and I'm just sitting here monitoring 0s, and when I get the first one I move to the next state. If I get a second one I move to the second state, and then if I get 0s I just stay in the second state. But if I get a 1 and then a 0, I'm going into the error state, or if I get 3 1s back to back, for example, or some third one, I again move to the error state. And so your property is very simple. It just says I should never be in the error state. And you're catching drop data, duplicated data, or added data, or reordered data, these types of data integrity bugs. Now, in most cases, there's some verification IP that you can plug and play, but the principles here are very important in that you can apply this to many other types of scenarios that you're trying to verify in your design. So very powerful techniques to apply in many different types of cases. A great application of symbolic variables is for config registers. You don't want the transaction of changing the config register. You just cut the config register, then you add some assumptions, one to make it stable, and then what are the legal values. When you run formal will run with one of those values. If you get a proof, it has analyzed all possible values. Formal can also drive undriven wires in your design. So let's say you're going to verify an encoder decoder that might be wrapped around a memory to correct for flipped bits. You just instantiate these in a wrapper. Formal is going to drive the input, which controls the outputs, all possible values here. And then in the antecedent of the property, what I'm doing is I'm saying the input that formal is driving here is either equivalent to what was coming out of the encoder, or the combination of both of these. There's a single bit that's been flipped or 2 bits that have been flipped. And then my property becomes the output must equal the input, either without any errors, with a single bit error, or double errors. So using the antecedent of the property, I can control what formal is doing and verify, in this case, an ECC verification. So these are both very powerful techniques in your formal test bench. There's many different ways to architect the formal test bench. Let's just take a look at a few possibilities. One technique is divide and conquer. So this is multiple formal test benches. So let's say you're verifying data integrity across this bridge design and you're getting inconclusive properties. Well, you might break this up into smaller pieces. So you could just verify the bridge itself with a scoreboard. And if this design is the same, then you're just verifying it once, you verify all of them. Or if there's differences here, of course, you would verify each one. Same thing on the crossbar switch. You've gotten some properties to make sure this switch is operating correctly. And then you can black box these things and do a connectivity check, for example. So this is one way you can divide and conquer the verification. Another way is brute force. By adding hard constraints, you can minimize the state space and then potentially get conclusive results. If you have enough licenses, for example, you can parallelize these runs. And so you set the selects here to very specific values and you're doing the verification. So this is another way to minimize state space and get the job done. Another better way to verify this whole design and create a much smaller formal test bench is to use some of the advanced techniques that we have been talking about in the previous slides. So we have our bridge here. The selects are stable during a transaction, so we can use symbolic variables there. Inside our formal test bench, we can just use one scoreboard, and we're doing end-to-end data integrity checking to make sure data comes in, it gets out the other side. And so what we do is we have some symbolic variables for let formal and non-determinism at the same time to let formal pick one of 4 inputs to go through one of 4 bridges to come out one of 4 outputs. So it's defining some path through this bridge. And when you run this, formal will figure out the values using non-determinism and the symbolic variables here to pick the path that has the bug, whether it's dropping data or adding data or those types of things, any kind of data integrity bug. And so you have a very efficient formal test bench. And if you get a proof on this, then you have analyzed all 256 combinations that you have on your select signal. So every single path through this design has been analyzed. So very powerful techniques. You can make a very efficient formal test bench and find these types of bugs. Of course, the age-old verification question is, how do I know when I'm done? Let's take a look. One of the primary areas where you are going to know when you're done with your verification is the test plan complete? And again, this gets back to test planning with formal simulation, what we talked about in some of the first sections of this presentation. So it's extremely important to have a complete test plan for your design. Also, what you're looking at is your assertions. Have you gotten full proofs, or are you limited by design state space to bounded proofs? And are those bounded proofs deep enough? If you inject random faults, do your checkers catch that? So you're kind of checking against your test plan to see if there's anything missing. So you're going back and forth, making sure your test plan is complete, so all the checkers you have tie into all of your test plan, but then you're also doing additional checks to make sure you haven't missed anything. And then of course there's coverage. So there's formal code coverage, there's formal property coverage, you have your cover statements. So you're getting a full coverage spectrum from your formal analysis. And then of course, ultimately for the design, some of the blocks are verified with formal, some with simulation, and you're combining this into a whole coverage picture to determine when you're done with your verification. Today we've talked about the importance of test planning to ensure the success of applying property checking to your verification. And this again ties into determining when you're done with your verification using your different coverage strategies. We've also talked about different formal test bench architectures and structures, the different components of a formal test bench, and we've covered some basic techniques as well as some more advanced techniques. Every formal test bench will be different. They're as unique as the person developing them and the type of design that you're going to verify. Doesn't matter if you're just starting out or you're an experienced formal practitioner, you need to start and grow from there. So discuss with your colleagues different experiences, different techniques, grow your toolbox, and start using formal in your design verification. Thank you for watching this presentation on demystifying formal test benches.